Okay, so now I was hoping someone would say, why is there a 2 there? Surely someone is concerned about the 2. Right? Physicists were so brilliant. Why would we derive and define B such that there's a 2 in the equation of motion? Wouldn't we want to get rid of the 2? Can't we define it differently where there's no 2? So here's the deal. So we're good at defining things. For convenience, we define a time constant. Basically, you can see that B over 2m is a time constant. That's what sets how fast this decays, and that's why it's the important number when we're solving a problem. But often we define the damping time constant as put those together. And we call it tau, and it's equal to m over b. Okay, not b over 2m, not 2m over b. We call it m over b, because that gives us something in seconds. So I'm telling you this because the book will talk about it. Sometimes problems will be in terms of a time constant, like on the MCAT, right? They may not give it to you. They might not tell you the value of b and m, and you calculate the time constant. They would just say, this is the time constant. Okay, they're trying to give you the time constant. So the factor 2 I meant to talk about was really here. Why don't we put a 2 in there so that it just turns into t over tau? Right? Why do we have it as t over 2 tau? That's what's weird. So we look at this. We looked at the amplitude. Right? We would say A equals A naught e to the minus. And if it's b over 2mt, it's 1 over 2 tau t. Right? T over 2 tau. So that's where the 2. Why would we leave a 2 in there? Okay? Why 2? I didn't mean to start talking about it so early. Now I've got like an obsession. Right? Why the 2? Okay, and the reason is we care more about energy. All right, so let's look at the energy decay. This is something we could ask you about. The energy decay looks like this. Well, it's 1/2 Ka squared is the energy, right, the total energy. So if the amplitude is slowly decaying, the total energy in the system is also decaying. I mean, you're losing it to heat due to the friction forces and due to the damping. So, so when it was undamped, just as a review, I'm not in sync with what I'm saying and writing here. E was 1/2 Ka squared, and it was constant. Remember, it was going between kinetic and potential. No, kinetic and potential. But now that it's damped, now we can write the total energy as a function of time, and we can see that it decays. It's 1/2 K, and now we have this decaying amplitude in there, A naught. A naught e to the minus 1 over 2 tau time squared. Okay. And maybe you can see what's going to happen. What happens when you square A naught? You get A naught squared. What happens when you square the exponential is you double it. The 2 comes in here and it cancels that 2. So that's why we define it this way, is what we care about is energy. So, and then you could even be really clever and say 1/2 K A naught is E naught. Whatever energy it had at the beginning exponentially decays at tau. E to the minus t over tau, like that. So that's why we define it that way. As we think in terms of energy, waves we're doing soon are treated in terms of energy. So that's tau. Okay? So a problem might give you B and M, it might give you tau, whatever. Now you know how they're related. Okay? When we could do a problem with this, it'd be exactly like this one. We could have said, how long until the energy decays to lose 1/2 its amplitude? And you'd go through the exact same math, except this 2 wouldn't be here. That'd be the only difference. So the amplitude and the energy decay at different rates, and that's because the energy depends on the amplitude squared. That's why they decay at different rates. And this is an idea fundamental not just in oscillators, but in waves and in everything. Anything shaking, the energy depends on the amplitude of the shake squared. Even if it's not in meters, whatever it's in, that's in general. Shaking things have an energy that goes as the shake squared. Okay? Okay.